is Hecke Algebras. Before I start, I wanted to make a very brief comment. There's an obvious question, which is, why are we doing this? And I haven't really addressed that yet. And in fact, I'm not really going to address that today. But so much. But I guess I'd wanted to say I'm hoping to address this a lot more in the next 2 days, but just maybe give a vague kind of map of some reasons why you might be interested in this, and I guess everyone here has some reason be here. I'd say probably the most important, certainly original motivation, is the classical Langlands correspondence, and by which I don't mean the kind of approximated thing I wrote yesterday, but I mean the Langlands correspondence for number fields, which is one of the, I think, probably one of the deeper things in mathematics, and which my goal in this week is not to mention at all. So I've already violated it. But this is sort of certainly where this is the original motivation. Geometric Langlands is as a fairly precise analog for over Riemann surfaces for the kinds of questions that the Langlands program for number fields asks. And if you're familiar with the Langlands program, it'll become clear, hopefully today, where those analogies come. What I would like to do this week is to try to motivate the Geometric Langlands program in other ways, rather than as kind of a playground for the Langlands program for number fields, which is, I think, a very good motivation. But there are other reasons. And I think maybe the next, historically, maybe one of the other next reasons is the kind of things we started seeing yesterday, that if you start studying these geometric Langlands questions in higher genus, you come up with some very beautiful geometry, which the Hitchin integrable system. There's a lot of connections between the geometric Langlands program, integrable systems, conformal field theory, which we might get to later today, and various other structures. So when you start asking this question for some reason, and then you find that it relates to a lot of very rich mathematics, and that gives you some motivation to keep going. I think there's sort of two, for me, I think the two most convincing motivations are, there's a motivation coming from representation theory. And by this, I mean representation theory of various kinds of objects. And this is going to be things like loop groups, quantum groups, braid groups, and assorted other things, including things like real Lie groups. And this is going to be my topic on Saturday. So it'll turn out that there's a local version to the geometric Langlands program where we forget about these Riemann surfaces and where we have a lot of strong ties to questions in representation theory. And that's one of the strong motivations. And perhaps I think the most convincing to me motivation is today is four-dimensional electromagnetic duality. So we found out in the last year or so, thanks to the work of Kapustin and Witten, that the geometric Langlands program can be thought of as a two-dimensional manifestation of a fundamental phenomenon in 4 dimensions. And so I think this is going to be my topic for tomorrow, and this, I think, provides a kind of intrinsic motivation for geometric Langlands without resorting to number fields. The geometric Langlands program itself, as I'll explain tomorrow, can all be seen as aspects of four-dimensional topological field theory. And in fact, it turns out that all 3 of these things are really part of the same story. So, I mean, it's not, you can think of this as really a big umbrella. It doesn't explain the number theory, so far, certainly. But anyway, so hopefully this will assuage some fears why we're doing any of this. OK, so now what I'd like to do is I'd like to actually introduce the geometric Langlands program, but I'd like to do that by first going back to the abelian case and reminding you of the way we describe line bundles as divisors, in terms of divisors. So how do we think of, so what is this picture? This is very familiar. This is kind of the local, if you'd like, in the case of a Riemann surface, which is where we live, this is a local description of pick x, where x again is a Riemann surface or algebraic curve. So what's this local picture? So suppose here's my x, and I have suppose I give you a line bundle L, a line bundle. The way I want to describe a line bundle is by I find S is a meromorphic section. So for any holomorphic line bundle, Riemann surface, I can find a meromorphic section S, which is going to have a finite set xi of zeros and poles. So we have a section of L that, away from the collection of these finally many points, defines a trivialization. We get a trivialization of L away from these finally many points. So this already gives us a lot of data to work with. We know that such a line bundle away from some finally many points, which unfortunately I haven't specified. I can't tell you which ones. But away from some finally many points, I've trivialized L. And what do we do next? We assign to L its divisor. So we just keep track. We assign the divisor of the section S. We keep track of the zeros and poles. So we look at the sum over these point xi of the order of xi of the section S. So this is the order of zero or pole. And then we realize that, well, I might as well be a little less efficient. Oh, thank you. Thank you. So I might as well be a little less efficient. I might as well say I'm going to sum up over all points in the Riemann surface of the order at this point x of S, because these orders are going to be zero at all but finally many points. So this is actually a finite sum, despite looking like an infinite sum. And so where does this live? This lives in a product over all points x in x of a copy of the integers, I guess times a basis element x, except that, well, it's not so bad. We put a little prime on this to say that at all but finally many points, we get 0. So these are the kind of sums we get. These are finite sums. All but finally many points, we have 0. OK, so this is great. This is very familiar. This is what a divisor is. But now, where does this let me try to say, what is the local origin of this divisor, or in particular of this z? Why do we have a z at each point? Where did this z come from? And the way the z came from is I want to think of the z in the following way. I can trivialize my line bundle away from these finally many points, but I can certainly also trivialize the line bundle in a small disk around every point. So I'm going to choose the data of trivialization of a line bundle on a small disk around every point. So now we need to kind of come to terms with what we mean by disk. And different people will mean different things by disk. So I think it's going to be safe to think of these disks as complex analytic disks for all purposes. The way I would like to think about them is the disk. A disk for me, I'll still think of it as a disk, but it's going to be the spectrum of the ring, which I'll call O sub x, which is so the disk at a point x for me is the spectrum of the ring O sub x, which is the ring of formal power series in a coordinate. Let me call that coordinate z. So by this I mean I'm taking a very, very small disk. I'm taking a disk small enough so that any formal power series converges. Because I'm going to be lazy later. That's a better notation. But, great. So I'll just drop this by the next line probably. So it's a very, very small disk, which makes it a little confusing when I make it even smaller, because inside of the disk I have the punctured disk. So what's the punctured disk? Well, I take the disk and I remove the point x. So that's the spectrum. Instead of having Taylor series that converge, I now look at Laurent series. So this is the ring K sub x, which is isomorphic once I choose the local coordinate to formal Laurent series in Z. So it has only finite order of pole, but again, infinite number of positive powers of Z. Okay, so this is going to be my local ring and local field at this point. And these are functions on the puncture disk, these are functions on the disk. But again, I think it's going to be safe to just take an analytic disk and just honestly remove a point. But this is how I'm going to think about this. And okay, so what does this have to do with anything? So if we have our section S, and together with, so suppose what's our data? Suppose I give you a line bundle L, I give you this section S, this meromorphic section, and I take these local trivializations on disks at each xi. So I take those little disks around my marked points, and I'm going to trivialize the line bundle at each of those points. So what do I have? What does this data give me? Well, if you use this trivialization, you write in the trivialization of my line bundle on this disk, S in this trivialization gives me an element of K sub x star. So I'm going to think of my meromorphic section near this point. In the trivialization, it's just a Laurent series, but it's non-zero. It's not the zero Laurent series. So it's invertible as a Laurent series. So what we get out of this, we get an element of the product over, for each copy of the xi, I get K sub xi star. So I'm just going to think of this data of my meromorphic section, giving me at each point a non-zero Laurent series at that point, which is the transition function between the trivialization away from the point and the trivialization near the point. Okay. So, and again, I can be less efficient. What I can say is if I take a line bundle L and I take a meromorphic S, section S, and now I'm going to do something a little absurd, which is I'm going to take local trivializations on disks at all points, x and x. So I'm going to choose a lot of data. I'm going to take my line bundle and I'm going to trivialize it near every single point. Then what do I get? Well, I get an element now, which is now a product of an invertible Laurent series at every point, except that at all but finally many points, I get something that's actually a Taylor series. So there are only finally many poles. So I'm going to put a prime here, which means that at all but finitely many points, our local expression, S in this trivialization, lives in O sub x star. So this is an invertible Taylor series. So in particular, one that has a non-zero constant term. Well, this is a Taylor series that can be inverted as a Taylor series. So your section only has a pole at finally many points, pole or zero at finally many points, and but the rest of the points, it's regular. So, okay, so this is this crazy space has a name. It's called the edels of X, or the multiplicative group of the edels of X. But I'm not going to stick to the Adel notation, but if you've, so A denotes the Adels, and this is the multiplicative group is known as the edels. So, but this is, what all this is doing is saying that I'm going to keep track of my local data in a very inefficient way. I'm going to keep track of all local trivialization at every single point, and my meromorphic section, and this is what that data gives me. So now, sorry? So now you can ask, why am I doing this? What does this have to do with divisors? Well, the point is that now suppose so now I've gone to this kind of extremely coordinatized world. Now let's go back. What I really care about is the line bundle. So let's start forgetting all these extra data. So suppose I look at line bundle and just the meromorphic section. Well, what have I done? I'm forgetting the change of this. I'm starting with this data. And I'm forgetting the change of the choice of local trivialization at every point. So now where does my data live? so here my local data, I look at a meromorphic section S. Local data, it lives where? Well, first, if I chose a trivialization, I get an invertible Taylor series. But now if I change that trivialization, I'm going to be multiplying it by a non-zero. So I have a non-zero Laurent series. If I change the trivialization, that corresponds to multiplying this by an invertible Taylor series. So now what is this group? This is Laurent series in Z. If I choose a coordinate, this is non-zero Laurent series, modulo Taylor series, the units in Taylor series. So what does this thing look like? This is, what's a non-zero Laurent series? It's some a n, sorry, that's a z. This is a z to the minus n plus a bunch of higher order terms. And this is up to things of the form b0 plus b1z plus so on. So up to rescaling by such a thing, the only thing I remember from a Taylor series is this number, minus n, is this leading coefficient. So the quotient of Laurent series by multiplication by Taylor series is just the integers. The only thing I remember after changing, the only local data I have from a section, if I don't pick a trivialization, is an integer. So this collection, L and S, it defines something which lives in the product over all points in X of invertible Laurent series modulo invertible Taylor series, which is exactly this product over X and X of the integers. So this is one way to think of the divisor of the section. Does this make sense? Okay. So we're going to. So the point is that this is exactly the group of divisors on X. And so this gives us this description of the Picard group. So we've described the Picard group. If you have line models plus meromorphic sections, you get such a thing. But now I can now think of the Picard group itself. So pic X itself. Well, this is the collection of just L's. I'm going to forget about the meromorphic section. So how do I forget about meromorphic section? I think of this meromorphic section as a meromorphic trivialization of my line bundle. So I now need to rescale. I need to change this data by multiplication by meromorphic trivializations. This has too much information in it. Let's mod out by change of meromorphic trivialization. So we need to look at divisors on X, this product of Z's, and we need to mod out by look at rational functions on X, non-zero rational functions acting by rescaling S. You can take this S, the ratio of any two sections S is given by something here, and I can rescale it. So what does this mean? This really means that any meromorphic function X gives a particular divisor. It's zeros and poles, and these are the principal divisors. So this is divisors modulo principal divisors. Okay. So this is a familiar picture, but let me just write it again in this kind of notation. It's the product of kx stars at every point. Modulo, I have these OX stars, and I have, actually maybe I'd rather write it this, sorry. I'll write it this way. So it's the product of Z, so it's Z, and I'm going to write Z as kx star mod OX star. And this is mod C of X star. So this is a description of the Picard group of X. And in fact, it's a description as a group. All of these are abelian groups. I'm just taking quotient of an abelian group by various subgroups of it. And maybe I should just give this thing a notation in case you are familiar with this kind of picture. So I'm going to think of Cx star as the group GL1 of C of X. It's invertible elements of C of X star. And Kx star, so Kx star, this is going to be the GL1 of the adels of X. And I'm modding out by GL1 of the ring of integers of the adels. So these are just notations for the same thing I have here. So if this helps, then that's good. Otherwise, I won't stick to this idyllic notation. OK, so this is the description of the Picard group that I'd like to stick with. So the Picard group has it as a group can be written as a double coset by doing this kind of, well, it's a lot of overkill, but this is how we usually describe line models, by divisors up to principal divisors. And these divisors are really giving a section and looking at its poles, which are its description and local trivialization. OK, so now I want to do the same thing for a non-abelian group. So if I give you a general group G, I'd like to get a similar description of bun G of x. So this moduli space of G bundles on X, I can repeat the exact same discussion. So the exact same discussion carries over. So how do I do this? Suppose P is a G bundle, principal G bundle on X. We're going to choose the following things. We're going to choose a meromorphic section, or if you'd like, a meromorphic trivialization of G. Of P. So maybe I should point out why do we do this kind of extreme choice is because I can't, if I give you a line model on a Riemann surface, algebraically I can't tell you away from which points I'm going to trivialize it. For different line models, if I take sections of different line models, the places where they'll have zeros and poles will be different for each line model. So if I want a uniform description for all line models, that's why I'm doing this kind of extreme thing over all points in the curve. So I don't have to tell you ahead of the time where I'm going to trivialize. So, so if I have so in other words, this is a trivialization of some finite collection of points x sub I. And so now I'm also going to choose, trivializations near each point, if you'd like, just the points x sub I, or if you want to be extreme, you can do this near every point on the Riemann surface. So what's my data? So if I have a G bundle and I have a trivialization near this point, and I have a trivialization away from this point, so this is supposed to be my picture. I have a trivialization on the disk and a trivialization away from the disks. What's the data I get? I get a transition function on the circle. So on the circle, I have the gluing data that's telling me how the trivialization outside and the trivialization inside are supposed to match. So that's a map from the circle to G. So, so we get out of this data, we get transition functions, functions or clutching data, which are in the topological setting would be elements of the loop group. And we can think of the loop group as some class of maps from S1 to G. So in this picture, I just think of a data on the circle telling me how to glue these. In the algebraic picture, the same kind of thing holds. I have a trivialization on this small disk, a trivialization away from the point, and I get a change of basis on the overlap, which is now an element of something I'll also call the loop group. It's G over this ring of this field of Laurent series, G of Kx, so in other words, G over Laurent series. So in the case of GLN, this just means a matrix. This just means a matrix of Laurent series, which is invertible. So my data at each point is a matrix of Laurent series. And that's telling me how to match the trivialization inside to the trivialization outside. And so now what does this tell me? So now I want to get rid of all these choices. So the change of the local trivialization. I want to get rid of the change of the local trivialization. So that means I want to see what happens when I rescale my trivialization on the disk. So these in the topological pictures, this would be something like a holomorphic map from the disk to G. As I think of this as a subset of the loop group, these are loops that extend inwards to the interior of the disk as holomorphic maps. So I'm going to call this L plus of G. So that's my analog of what before we had OX star in the GL1 case. So these are maps that extend inwards, or in the algebraic setting, this is going to be G over the ring of Taylor series. So this looks like G in a local coordinate G of, so it's a matrix of Taylor series, which is invertible as such, sitting inside of G of kx. So this is my change of trivialization. So now if I look at my bundles up to, so I learned this trick yesterday. You're allowed to go circularly. It's exciting. So in other words, this tells me, so maybe one more thing. What is the change of the meromorphic trivialization? Well, it's the same kind of thing. If I have this trivialization away from defined rationally, if I want to rescale it, I multiply by an element of G with coefficients are now rational functions on x. So this is just a meromorphic map from x to G. And so this tells me, so this is telling me how to change this meromorphic trivialization. And as a result, I get a description that's, I believe, due to initially to Andre Weil, is that the set, that bun G of x, as a set at least, is given by the following double quotient. The product of G of kx mod G of OX. So I'm going to think of it this way, or you can parse it also as a product of these modulo the product of these. Does this statement make sense? So this is a summary of what we have. A G bundle, if you take all these local trivializations, defines a bunch of meromorphic data, transition functions on each point, and now we're going to get rid of the change of transition functions on each disk, and we're going to get rid of the change of transition functions generically. So that's where this, that is, I guess what I haven't explained is the converse. If I give you such transition functions, I can use them to define a G bundle. I just glue together all these trivial G bundles on all the disks with a trivial G bundle generically using these gluing data. So the point is that this is actually a bijection. Okay, so this is the description of bun G of x, kind of adelic description of bun G of x, and which is, yeah.
So this is the level of points.
This is a level of points. It can be made stronger. I mean, this is true in, can be done in families as well. But so I'd rather keep it right now as a point level statement. But I can do this over families as well, so it has some algebraic structure to it. I mean, this doesn't look like a very algebraic description because it's so big, but it does have some algebraic structure to it. Right. So I mean, I really, this is going to be true in families as well. This is a statement of, but right now yeah. Let's just take it as a statement about the complex points of x. But this is going to be a statement about the stack of bundles as well. This is going to give you the families. You can put in, instead of doing it over C, you can put in some other ring. Okay, but in any case, Weil stated this as a statement on the level of points. Let me point out that this seems very extreme, and indeed it is extreme. So if we're in one of the following two settings, if G is semi-simple, so e.g. we have SLN but not GLN, so for example not in case of rank 1, or we're in or if we're working in a complex analytic setting rather than algebraic setting, this is overkill. We can trivialize any bundle P outside of just a single point, x and x. So we don't need this extreme. The reason I did this extreme thing because I didn't know where I can trivialize. And in algebraically, in general, I won't know. But if G is semi-simple, and this is a theorem of Grinfeld and Simpson, or if I work analytically, then I can trivialize, and I get a much more efficient description. Bun G of x is given by, just look at this loop group, or G of kx, mod its positive half. So I just do this at a single point x, and then I mod out by changes of trivializations away from x. So in other words, I take my bundle, I take my favorite point x, and I trivialize the bundle away from this point. I trivialize my bundle near this point, and I just have a single transition function. And I need to worry about the changes of the two choices. So this is much more efficient, but unfortunately it can't be done algebraically even for line bundles. Yeah, so these are maps from x to x minus x to g. These are so this is g over the ring of, this is an affine curve. I could just think of g over the ring of functions on x minus x.
Okay. You still have to choose a meromorphic section.
Well, the point is that I can choose a section that has a I can choose trivialization away from a single point. That's the content here. That I can trivialize it away from just a single point. Lx, L plus. This is L plus. This is the positive half. So this is what I was calling G of. This is the loop group, and this is the positive half of the loop group. Okay. So this gives me a description. So now, so this gives me a kind of. It might not be very. Right. This seems relatively concrete. This might not feel very concrete. But the question is, well, but this is how we describe line bundles anyway. This is how we describe line bundles as divisors. Divisors, mod principal divisors. But in line bundle case, we had a huge advantage that Z, as we know, is a group. The local data describing line bundles were a group. And in fact, this double quotient construction was this double quotient of groups. I mean, we have an abelian group and we have two subgroups, and the quotient itself is a group. So pick was a group. Here we're in a non-abelian setting, and these are definitely not normal subgroups. We're just taking a group, and we're taking double quotients for two subgroups. So this doesn't have a group structure. And the local data, so what's the analog of Z here? The local data is something called the affine Grassmannian. And so this is LG mod LG plus. Oh, I guess, did I put the where did I put the plus? L plus G. Or I'm going to write it as G of KX mod G of OX. So this space, which is going to be kind of the main star today, this is called the affine Grassmannian. And I'll say what it looks like soon. But this space is not a group. It's just a homogeneous space. And this is what the analog of Z is. It's the local data at a point X. You're taking a trivialization on the element of the group on the circle, and you're modding out by change of trivialization. So this thing is not a group. So the question is, how do we use this? How do we?
In the right context, the Z was actually the order.
Right. It's going to be some kind of order, but we're going to describe this much more precisely soon. So this is some analog of the set Z in the non-abelian case, but the point is it's going to look like a Grassmannian. It's not going to be a discrete set of points. And it's not going to be a group. And now you can ask what another feature of Z, not only is Z a group, oh, probably didn't want to erase that. Not only is Z a group, but also Z acts on pick. We have this Z at a point X, and it acts on pick just by you add, 1 times X to the divisor. So if I have a Z, and I think of this Z sitting at a point X and X, I can take the divisor of a line bundle and add 1 to it at a point. So if I have a line bundle L, I can get a new line bundle, L of X, which is the line bundle, so defined, I allow sections of L to have a pole. I have a first order pole at X. That defines a new line bundle. And that gives me an action of the z. So, of course, well, of course, that comes from this description that pick was really the product of z's over each point x and x modulo the principal divisors. So you could just act by each of these z's. So there's a huge amount of symmetry to this, to the Picard group. And, well, in fact, this is in some sense, this, you can think of this as where the group, this is where the group structure of pick comes from. So another way to say this is, let's return to the Abel-Jacobi map. I'll write it slightly differently than yesterday. There's an Abel-Jacobi map. I'm going to think of it as a map from x now to pick, put it in degree 1. Yesterday I put it in degree 0. Pick 1 of x, which sends a point x to the line bundle O of x. So I just have a divisor which is 1 at the point x and 0 everywhere else. And so this is this gives me a set of points, and in fact this is an embedding of x into pick 1, and these points, or the image of this map, generate the group pick x. You could think of all the group structure of pick x coming from this. Pick x is generated by this collection of z's at points x and x. So here it's sort of maybe a nicer geometric picture than thinking of that discrete collection of z's. I have pick 1, which looks like this, and then I have my Riemann surface sitting inside of it some way. And it's sitting in some kind of nonlinear way, and then it generates the entire group. So all of the group structure of pick and all of its symmetries are given by these z's. So the question is, how do we proceed in the non-abelian case? In what sense is GER look like a group, and in what sense does it act on bund G? And that's what we're going to do. So in some sense this is a group, and in some sense it acts on bund G. And this is where the Langlands program comes from. Questions so far? Yeah.
How is it possible for that to be an inclusion? I mean, say x is P1.
Yeah, so this inclusion if the genus is 1 or bigger. Yeah. Right, thank you. Okay, so how are we going to do this? And I'm going to do that. I want to take, I want to make a diversion, and I want to discuss Hecke algebras. Kind of a general. So this is a general pattern of how to get symmetries, how to squeeze symmetries out of a situation where you don't have a group, but you have something like a coset space. So we don't have a group, unfortunately. We have a coset space, and I will describe this affine Grassmannian a lot more concretely in this next hour. But for now, I just want to say, what are we supposed to do? And what we're supposed to do is can be read off just by thinking about finite groups. So kind of, what are Hecke algebras? So I want to start first with kind of a toy model. Suppose G is now a finite group. So if I have a finite group, how do I usually study it? I study it using the structure of the group algebra. So how do I think of the group algebra? I have this kind of diagram. If I look at G cross G, it has 3 maps to G. We can project on the first factor, we can project on the second factor, or we can multiply. So this diagram, so if you did the homework from the first day about how to multiply matrices, the same exercise tells you how to multiply functions on the group. So the group algebra, which, how do I denote it? I guess I'll call it CG. So CG, I'm going to think of this as I said, I'm going to think of this as functions, complex valued functions on G. But I'm going to give it multiplication by convolution. I'm going to give it product f star G, which is I'm going to sum up along the fibers of mu pullback of f times pullback of G. So this is exactly how you define matrix multiplication. But now we're thinking of this as functions on G, and we're using the multiplication map on G. So you take the function f, you take the function G, you put them both as functions on G cross G, and you multiply, and then you sum up over the fibers of the multiplication map. Okay, so now, great. Now, so this is an associative algebra, but it won't be commutative unless G is commutative, unlike the pointwise product of functions. Okay, so now what else can you do with this? So suppose I give you a subgroup of G. Suppose I give you any subgroup of G. I can associate to this something called the Hecke algebra, which I'll denote Hecke of G and K. So what's a Hecke algebra? This is K by invariant functions on G. Or if you'd like, it's the group algebra, and you look K cross K invariant. Or if you think of this is functions. What does it mean? So K is acting on the right and on the left. So this is functions on the set of double cosets. So it's functions on G that are invariant both under the right and the left actions. So it's functions on the set of double cosets, and by definition, it's a subset of the group algebra. These are certain functions on G. But now I want to claim that this is not just a subset, this is actually a subalgebra. For any subgroup K, this is a subalgebra. And it's a subalgebra. You can just check that K by invariance is closed under the convolution product. Or you can, I don't know if this is helpful, you can just take the exact diagram we have up there, and you can put mod Ks all over the place. So I can write a kind of diagram like this, where I just mod out by K kind of every time I see a G. So I look at K, I put lots of these things, and I have these maps. And on top, well, I have a G and a G and a K, and I need to take the product over K. So I take the product, so I identify, so what does G cross G over K mean? This means it's kind of like a tensor product, where I'm allowed to pass elements G1 and, how do I want to write it? Let's write it this way, KG2, I'm going to identify that with G1, K, and G2. I'm allowed to pass the K through, just like a tensor product. Okay, so the point is I can just put, so this is a diagram of spaces. If I look at that diagram of maps, I can then project it by Ks everywhere. All the maps are still well defined. And the Hecke algebra is defined by the exact same formula for this picture. You take a function here, a function there. This is just a fancy way to say bi-invariant functions on G, and you do the exact same operation. Okay, so that's a Hecke algebra. So now you can ask, why would you do such a thing? So what's the meaning of Hecke algebras? What's their role in life? And there's many ways to answer this. They're all boil down to the same thing, which is they're the answer to the following question. How do I say? If W, well, this is one way to say it. If W is a representation of the group G, and I take the subspace of K invariants, this is K invariants, I can ask what acts on the subspace of K invariants. The group G doesn't act anymore. Well, the group K acts, but it acts trivially. So you can ask what's sort of the best thing you could do? What's the kind of universal answer to acting on the space of K invariants? And the answer, I've already given away, is the Hecke algebra GK. This is an algebra that will always act on the K invariants in any representation. So maybe I'll just kind of briefly maybe indicate why that's true. You can think of this functor from representations to the K invariants. It's a functor from representations to vector space. You can take the adjoint functor. And so in order what does this mean? There's a very nice representation, which is the induced representation from induced representation of the trivial representation from K to G. The induction is the adjoint of taking invariants, and it has a concrete description. It's just functions on G mod K. Functions on G mod K have an action of G by left multiplication. And I'll think of that as a representation. I'll call it this thing. Or I can also think of it as function, the group algebra of G, and I'm going to tensor over the group algebra of K, one-dimensional representation. So this is a representation of G that's generated by the trivial representation of K. It's kind of the universal thing that's generated by trivial representation of K. And if you think a little the abstract nonsense of it, you get that the hum as G representations from VGK into anything is the space of K invariants. That's kind of its defining property. And so now what does this, because you think, well, this representation is generated by a vector, a single vector that's K invariant. So all I need to do to give you such a map is tell you where in W it goes, and it has to go to something K invariant. So how does this have to do with Hecke algebras? So the point is that if I look at endomorphisms, so endomorphisms as a representation of VGK, that's an algebra, right? It's endomorphisms of something. But what is it? Well, it's by definition, this is hom. Let me just write it as hom G from VGK to itself. But that, by this universal property, that's the invariance of VGK, which is just functions on, well, VGK was functions on this homogeneous space, and we're looking at invariant functions, K invariant functions, so you get functions on the double coset, which is the Hecke algebra. So the Hecke algebra is the universal, kind of some universal object that will act, it's exactly the thing that acts on the invariants. I mean, it's endomorphisms, if you'd like, of the functor of invariants. This is kind of the fundamental property of induction.
So you get hom of this left-hand side is equal to hom over K?
No, hom over vect from, yeah, sorry.
Hom over K?
It's called Frobenius reciprocity.
Yeah.
It's Frobenius reciprocity.
So maybe that simplifies to the, because it's just the adjoinness of
Yeah.
It's
and
that
that will give you
Yeah, it's the
addition of two hom sets.
right. So this is hom from the trivial. This is hom K from the trivial representation of K to the restriction to K from G to K of W, which are invariants. So maybe let me leave that as an exercise. So this is, in any case, this is the fundamental reason for Hecke algebras. They're the thing that acts on invariants. Let me just say this exact same words geometrically rather than algebraically. So what's the geometric version of this? If I have a space X on which G acts, so now let's think in geometry. If I have a space with a G action, I can take the quotient X mod, not by G, by X mod K. And I can ask, what acts? Well, if I'm living in the world of groups, the only thing that will act is the normalizer, and there might not even be any normalizer to K. But now I want to think, well, not what acts on the, what acts not on the level of as a group action, but what will act by correspondences. So if I think of X times G, what does it mean to have a group action? This is something that has two projections to X. You project onto the factor or you act. So the same kind of thing I could do if I go to X mod K, I have a natural correspondence over X mod K, which is X cross G mod K, where I do the same quotient over K. And this again maps from X mod K to X mod K. So this tells me that if I have a group acting on a space, I get a natural correspondence on X mod K. I don't get a group acting, but I get a natural correspondence. And so this means that if you pass to functions, if you pass to the level of functions, as we said, functions are, the nice thing about functions is you can pull them back and push them forward over a correspondence. So we get that functions on X mod K carry an action of functions on K mod G mod K, which is the Hecke algebra, which is functions on K mod G mod K. And in fact, this is the same statement we had before, because this is just functions on X take the K invariants. So if you don't want to think about this algebraically, you can think just geometrically. If I have a group acting on a space and I take a quotient, I still get something. I get a natural correspondence. And that correspondence gives me operations on functions. I could take a function here, pull it back, multiply by a function a k invariant function on G mod k, so if I have alpha in the Hecke algebra, and I have a function f here, I put alpha here, I pull back f, and then I integrate the product. I take the integral of pullback of f times alpha, and that gives me an action. So that's how the Hecke algebra acts. Okay, so so this is what Hecke algebras are for. They're the natural symmetries of quotients. If you have a group G and you have a subgroup, this is what symmetries you get on the quotient. So now I'm going to pull a nasty trick and say that replace finite group by algebraic variety and replace functions by derived category of D modules. Okay, so the claim is that the same picture holds for any good theory of functions. So what does it mean, a good theory of functions? It means something like, for example, cohomology or K-theory, or these derived categories. This just means something where I have a notion of pullback, a notion of product, and a notion of integration. That's all I used. And so if I do this, so I now take, so now the claim is, let me summarize that. That trick, I guess, probably don't want to get rid of that. If G is now going to be going to be an algebraic group, or any really kind of algebraic object, I'm going to look at the analog of the group algebra. So what's my analog of the group algebra? It should be functions on the group. So my notion of functions now, I'm going to take, you can take K-theory or you can take cohomology if you have some properness, but I'm going to take the derived category of D modules. Now, and the point is that this is a black box that has the formal properties of functions. We can do with it operations of pull back, tensor, and push forward. This is going to be our version. It's a version of the group algebra. And the point is that this gets a convolution operation. By the exact same diagram, once you know that you can tensor, pull back, and push forward, you get a convolution which is an associative, or more precisely, this is an example of a monoidal category.
Are you saying that the derived category of D modules
Yeah.
on the algebraic variety G?
Yes, that's right. So the point is that if I have an algebraic variety G, I don't have a measure. I don't want to think. So if G wasn't finite before, I would need some kind of measure to integrate. I'm in an algebraic context. I don't have a measure. I still want to be able to integrate. And one of the contexts I can do that in is this. Why this particular context? Why am I not just saying take cohomology or some kind of property supported cohomology or something like that? And the motivations for that come, for example, from representation theory. Like why this is my notion of functions rather than something else. We can disagree about, but the point is that this is something that I can apply, have these nice formal properties.
Are these D modules in some sense properly supported?
No, but I need to be careful when I define push forward. Okay, so this is going to be and the same thing will hold for Hecke algebras. So this picture, by the way, that I'm explaining, this is taken from the book of Beilenson and Drinfeld, quantization of Hitch and Hamiltonians. But so let me just say another statement. If X is algebraic, X is some variety on which G acts, and I look at X mod K, and I look at functions on X mod K, this is my functions on X mod K, it's going to carry an action of the Hecke algebra. So now, what's my Hecke algebra? And now, my Hecke algebra is going to be, well, it's bi-invariant D modules on G. So this is going to take some care to define. This is what's known as equivariant derived category. More usually, it might be written as K equivariant D modules on G mod K. But the point is that if you think of K mod G mod K as a reasonable space, you could put D modules on it, and for the exact, I didn't use anything about finite groups. I just used the properties of these diagrams of pull back and push forward. You just copy the exact same reasoning. This will be, again, a monoidal category. In other words, this is our version of associative algebra. It has an operation, star, convolution operation, defined by the exact same formula. And it'll act on this space of functions. Okay. If you don't like this derived category of D modules, you should replace this by your favorite other theory. And so it could be various kind of cohomology theories or K theories, various motivic things. There are lots of things you can put in here that have these kind of formal properties, and you can repeat everything I say in those contexts. But this is the context in which the geometric Langlands program is developed. So now,
The monoidal category.
So what's so objects in this category
right,
you
give you functors. That's right.
this category?
That's right.
And what do arrows?
Well, there's a functor, if you'd like, there's a functor from this to what does an action mean? It's a map to endomorphisms. Right? So an action of this on this means a map from this to endomorphisms of this. So it's a functor from, it's a monoidal functor from this category to endofunctors of this.
So is this bounded derived category?
I probably should put bounded, yeah. But,
Then if K is
yeah,
very bad, then will you not run into problem with push forward?
definitely. So I need to be very careful of what kind of Ks I applied this to. I need to be careful of taking push forward with proper support. But I'm going to ignore that. So this is a very abstract picture, and I'm going to apply it in a second in a very specific situation where I'll tell you what all the things look like. But this is just the point is that this is a completely general pattern. It's just do what you do for finite groups, do it in this context, and now we have to see what does that mean and what does that actually tell you, and that's what I'm going to explain. But yeah.
The monoidal category has a K theory. Has K theory.
Absolutely. So you can just take the K group of this category, and that's going to be an associative algebra. And you can just replace this by that on the associative algebra, which is K group of this. Absolutely. So that's a safe thing to do. Okay. So now I'm kind of out of time. So let me just state what is this going to give us, and then we have to work out what this happens. So the claim is now that this tells us that the space bun G of X, this modular space of bundles, has a huge amount of symmetry. We described it in terms of a double quotient space as G of monomorphic functions mod this product of all of these loop groups and we quotient it out by all their positive halves of the loop group. Now, this is not a group anymore, but it's certainly a quotient space by a group action. It's a quotient. It's something of the form X mod K. So rather than think of it in some extreme way, I want to say that for every, so what do we get out of this picture? For every point, X and X, every time you give me an X and X, I'm not going to worry about this whole thing all at once. I'm just going to think of a particular factor. For every particular factor, this space is a quotient of something by the positive half of the loop group. So if I just omit one of these factors, I get a space on which the whole G of Kx acts, and I've taken its quotient by G of Ox. Okay? So I'm just going to, if you'd like, let's just focus on this part for some particular x. If I remove this, I have a right action of G of Kx, and I've taken the quotient by G of Ox. So this tells me for every x and x, I get an action on this crazy thing we've been looking at, this space of functions on bun G of something called the spherical Hecke algebra. And what's the spherical Hecke algebra? It's, in this context, it's you look at the loop group, you mod out by its positive half, and you take double cosets for the loop group and its positive half, and you look at functions on double cosets. So I'm going to look at functions on double cosets, that's going to have a convolution structure by this abstract nonsense. So this is going to be some associative gadget. And it's for every point x and x, these are the natural symmetries. Or if you don't like, forget about saying all these words D modules, and I'll write this explicitly in the next hour, for every point x and x, we get a natural correspondence. And then you could do to that correspondence whatever you like. Apply to it any theory you like to do to apply to correspondences. But for every point x and x, we'll write a correspondence. And what we're going to do in the next hour is going to say, what are these correspondences look like? What do they mean geometrically? And we're going to explain the main miracle of the story, which is that this thing is actually commutative. And that's kind of the key point of the Langlands program, is in some sense, is the commutativity of this algebra. Okay, thanks.